Hello friends, welcome to our channel. Let's have a look at problem 1718. Construct the lexicographically largest valid sequence. In this video, we are going to explain a solution based on the strategy of backtracking. So here, let me quickly overview the requirements of the problem. So here we are given an integer n. We want to find a sequence that satisfies all the following conditions. First, the integer 1 occurs once. And the second, each integer between 2 and n occurs twice in the sequence. So the first two items actually determines the sequence length given the n. The last one is that for every integer I between 2 and I, the distance between the two occurrences of I is exactly I. So this one is an important one. So here we want to return the lexicographically largest sequence. So here actually you need to understand what do we mean by lexicographically largest sequence here. So here is actually position-wise comparison of the number. So for example, sequence A is lexica larger than sequence B. If let's assume they have the same length. So if the first position they differ, then sequence A has a larger number than the corresponding number in sequence B. So this actually gives us information like this. For example, 12, 2, and 2, let's see, is greater than this one, say 2 and say 3. The reason is that this 12 is greater than 2. But if you regard them as strings, so here 12, 2, and then you have 2 and 3. So as a string, actually this 2 is larger than 12 because this is begins with 1. So the latter actually is larger in the Euro sense. So here, in the sense of the current problem, right? So this is the one important thing to notice. So what I mean by lexica larger? So this is the one. The second one actually is the length. So given n, right? So we know 1 appears once, so you have a 1, length 1. And between 2 and n, the number is n minus 2 plus 1. So each number appears twice. So this is the overall length. That is n minus 2 plus 1, right? Not n, 2 times n minus 2 plus 1. That is 2 times n minus 1. So this is also important to notice. So once we have these two pieces of information, and also if we know the problem solving technique called backtracking, so this problem should be straightforward. So now let me present the backtracking solution. So here notice that n is in between 1 and 20. So 20 is a larger bound of the problem size because we are trying to assign all the positions, right? So that's why here we have 20. It's a relatively small number. So in order to do this, what we shall do is first, I'm going to get the length of the sequence. It should be 2 times n minus 1, right? So this is the one thing. And also we want to construct a sentence. So we sequence. So we have this sequence length. And also we can use a set called sin. So let's see, this is the set. Then what we want to do, we want to write a, actually it's an iterative recursive DFS function. Let's call it define backtrack. So starting from index I, you can think of index I to be 0, 1, 2, up to length of sequence minus 1. Once the I equals the sequence length, meaning that we're finished the assignment, we can return. So now let's look at this. So if I equals length of sequence, so this is the stopping condition or bounding condition. So we just need to return true, meaning that we can finish the fill all the positions in this sequence, and then we just need to return the final state of the sequence, right? So this is the one. Another thing is that if sequence I is used, so because we assign them to be 0, and then if it were not 0, it means that it already used, then we are going to try next. So we're going to try to assign a next position, backtrack I plus 1, right? So then this is the two bounding conditions or stop conditions. So now let me also, we need to incorporate this lexicographic sequence. So for this, we are going to do the iteration or assignment in a reverse fashion. Before we do this, actually, let me give you a walkthrough of example 1 so that you know there are some subtle cases. Walkthrough of example 1. So actually, if you look at this one, you should already notice what I mean. So here n equals 3. So the length, of sequence should be 3 times 2 minus 1, right? That is 5. So we have a sequence that is 0, 0, 0, 0, 0. Then I want to assign it. So first I want to assign 3, right? So if I assign 3 here, then the next 3 will be 3 far from this one. So 0, 1, 2, 3. So we should assign it here, right? Then I want to assign 2. So it's the first, let's see. Let me write like this. Sequence equals 0, 0, 0, 0, 0. First assign 3. So we get this such a state. So now we need to assign 2. So now let's see what's happening. So we have 3, 0, 0, 3, 0. Ideally, we want to assign 2 here. But if you assign 2 here, you need to assign this one also to be 2 in order to satisfy the third bullet item. But 3 is already assigned, right? Then we cannot assign 2 here. So let's restore here. We check next. That's what I mean here. So we should assign 2 here. And then this is the index 2. So we should have assigned and another 2 at index 4, right? This is the case. So now we just have 1 remained. So we just assign 1 here. Let me write one more step. Assign 1. So we are going to copy this one. And then we assign 1 here. That's it. That's the final state. So this state should be unique, actually, in this problem. So that's actually, this walkthrough explains this one. So now let me also take into consideration of lexicographically largest into consideration. So how do we do this? So we need to iterate in a reverse fashion. So this is especially due to the definition of lexically order, right? So let me use num in range. So the largest is n, right? The smallest is 1. So we here write 0, but the step will be -1. So then I want to check if num in used or in sim. So in this case, it means that we have already finished the filling the positions of nums, right? So we just continue. So this is one situation. So otherwise, this current number hasn't used yet. So we want to assign this current number at current index I, right? So now, in order to do this, we need to also notice that. So once this current index I assigned num, so the next index, that is, next index will be the current index plus the num itself. And so if num does not equal to 1, because if 1, we just make the next position to be itself, right? So then we need to check if this position is used or not. If it were used, still we cannot finish the task, right? If next is greater than or equal to the length of the sequence, actually it's equal, right? It's greater than, because if we just it can be very large, out bound. So or the sequence next does not equal to 0. So the first condition is auto bound if I want to assign, because this can possible. For example, here you cannot assign 3 in the last position, because the next 3 will be auto bound. And then the second condition is that the next index is already used. Because of this, we can also not assign the current number num into the index I. So in this case, what we want to do, we just continue without doing any assignment. So otherwise, because this condition, we passed this if condition, it means that the current position and the next position in the sequence are both not set yet. And because of this, we can try to assign. So sequence I and also the sequence next, we set this to position to be the current num, right? Then because we assigned this, so the current number is used. So we then add to be num, right? Add this one. So now we want to check if backtrack I plus 1. If this can be done, so we just need to return true, right? So this is the check. Otherwise, we need to do the backtracking step. So how do we do the backtracking step? So here we do the assignment. So we need to make them back. So sequence I to be sequence next. So originally 0, 0. So we need to send to be 0. Also, we need to so here used. So let's see. It might be better to use used, but let's see. So here then we want to remove this num, right? So this actually from here, this assignment and this one. So I guess you should be able to see the pattern of using backtracking. So now what we want to do is after all those, if nothing has returned, so we actually just return false, right? So in this case, actually here in this problem, so it says that it's guaranteed that at the given conditions, there always a solution. In other words, this actually is redundant in terms of the assumption of this problem. But here, for this coding, it's necessary because, for example, here we have some checks, right? We need to return this false. So now what we want to do, we call the backtrack. And then we just need to return the sequence. So that's what we initially used as 0, initialized as 0. So now let me first do a test and then do some comments. So either, let's see, what's the problem? Name I, let's see. Backtrack, this I, let's see. Backtrack. So here I guess I should backtrack 0. So let's run. Yeah, it passes the 2 test cases. Now let's look at the generic case. Yeah, it passes all the cases. So here let me make some comments. So for the current problem, so given the n, actually the length is determined, right? So that's one part we need to notice before doing the coding. The second is that we need to pay attention to the definition of lexicographically larger, right? This definition actually determines this part, so how we do the coding, right? So the third one, walkthrough of example 1, basically tells us that there are such conditions, right? So afterwards, actually in this coding, in this hyperfunction, so you notice that, so here, this toLang and this toLang assign and add to the same set and on set and remove. This is the standard backtracking paradigm. So with that said, I guess that's about it for the current video. You are welcome to walk through other problems in our channel. There are many playlists. And also, if you find this video is of use, you can share with more friends so that we can encourage more practice. Thank you.